Hello, my name is Oier Mees and welcome to my presentation on learning object placements for relational instructions by hallucinating scene representations. This is joint work with Emek, Johan Vertens and Wolfram Burgard. Robots coexisting with humans in their environment and performing services for them need the ability to interact with them. One particular requirement for such robots is that they are able to understand spatial relations and can place objects in accordance with the spatial relations expressed by their user. For example, in this image, the user asks the robot to place the mug on the right of the box. But how do we define an object placing location? Usually, from spatial relations alone, it is not possible to know at which exact location a user would like to place an object in relation to another. The definition of a spatial relation, such as right of, could also change from one user to another. In this example, all of this region could potentially be a valid placement for right of the box. Ideally, for a given relational instruction, we would like to be able to have a pixel-wise probability distribution from which we could sample an object placing location. However, one of the key challenges to estimate such pixel-wise spatial distribution is the lack of ground truth data. This originates from the inherent ambiguity on modeling such ground truth distributions without using heuristics. So how can we come up with a model that can predict pixel-wise probability distributions for different object-based spatial relations? Let's start with the case of detecting relations in an image. If we have an image representing the context and two bounding boxes for the objects, we can train a classification network to predict their relation. In this case, we have a ResNet 18 that predicts that the blue cup lies right off the orange cup. To improve performance, we replace the bounding boxes with attention masks characterized as Gaussian distance transforms. However, if we want to place an object in relation to another, we do not have both objects on the scene. Thus, we need to imagine what spatial relation both objects would form if the object to be placed was placed at different locations. Given this ball, what relation would be formed if we put this red sponge here, or there, or over here? So how can we simulate such scenes? Well, what if we would simply paste the objects into the image? Pasting objects would enable us to use the aforementioned classifier to know what relation the object would form if we chose a given placing location. However, naively pasting object masks in images or in painting is computationally expensive, noisy, and requires segmentation masks. Moreover, it creates subtle pixel artifacts that lead to noticeably different features and to the training erroneously focusing on these discrepancies. To sidestep these issues, we propose implanting high-level features pertaining to an object to trick the classifier into classifying a hallucinated scene. In this case, we could, for example, ask the network what relation an imaginary object placed at the red circle would have with respect to the orange cup. And it would then say that this object would be in front of the orange cup, for example. We make use of this technique to develop our full approach, which can predict pixel-wise object placement probabilities for a set of spatial relations from a single input image. Our spatial RelNet network, which is based on the fast semantic convolutional neural network architecture, processes the input RGB image and the object attention mask to produce pixel-wise probability maps gamma over a set of spatial relations. During training, we sample object placing locations according to gamma, implant inside the auxiliary network RelNet at the sampled locations high-level features of objects, and then classify the hallucinated scene representation to get a learning signal for a spatial RelNet. At test time, the auxiliary network is not used. To evaluate our approach, we recorded a dataset with a total of 1,237 images, around 140 tabletop scenes, and 5,304 relations. To help our approach become less sensitive to viewpoint changes, we recorded the scenes from multiple viewpoints, ranging from object-centric to top-down with a Kinect RGBD camera. We annotate the recorded images with bounding boxes under pairwise spatial relation information. Here are some qualitative results of our approach. Despite having no direct supervision or heuristics, the predicted heat maps are consistent with the expected distributions. There are two behaviors that the network seems to have picked up. On one hand, it scales the predicted heat map to the object size, as you can see on the heat maps predicted for in front over here. Second, and most interestingly, the network has used the context to implicitly learn object affordances. It discriminates that on some container like here, placing inside is possible, and therefore not to put an object on top of it. For flipped containers, on the other hand, it predicts more probabilities for putting an object on top of it rather than inside of it. We also try to do a quantitative evaluation of the predicted heat maps, which is difficult without any ground truth probability maps. Due to the inherent ambiguity of defining pixel-wise spatial relations, we asked 3 users to use a spray tool to draw points in which placing an item would reproduce a spatial relation. Here you see an example of the GUI. After the user draws the points with the spray tool, the points are convolved to generate a dense probability distribution. Inspired by metrics from object detection and segmentation, we threshold the distributions at different ranges and compute their mean intersection over union, also known as IOU. Here you can see an IOU of 0.39 is computed for the threshold of 0.5 for this example. Here you can see some results for the IOU metric thresholded at levels 0.25, 0.5, and 0.75. Overall, our method yields good results, though relying on a weaker form of supervision. In the paper, we have more results with other metrics that compare distributions, such as the KL divergence or the Kruskal-Wallis statistical test. Finally, we performed a human-robot interaction experiment.
Working on it.
Our study involved 11 participants recruited from a university community. Each participant was asked to give 20 natural language instructions to our Peer 2 robot, which were then parsed with an Amazon Echo Dot device. For each placement trial, the participants were asked to choose a reference item from a range of 30 household objects and to place it on the table at a random location. Next, the participants were instructed to choose a different item to put on the gripper of the robot.
What else do you want?
Afterwards, the participants were asked to provide a natural language instruction that contained one of the 6 spatial relations used in this work. After sampling a location from the predicted distribution, we used the robot's Axus Ixion RGBD camera to localize the pixel coordinate in 3D space. Our system then planned a top-down grasp pose to the calculated 3D point. Overall, our approach can effectively learn object placements for relational instructions, as you can see from this video.
Robot, place the ball right of the banana.
All right, working on it.
Robot, place the lemon in front.
To conclude, we presented a novel approach for learning object placements for relational instructions from a single image. Our main contribution is a method that leverages auxiliary learning to overcome the problem of unavailable ground truth data by classifying hallucinated scene representations into a set of spatial relations. Finally, we exemplified how the distributions produced by our method enables a real-world robot to place objects by following relational natural language instructions. Thank you for your attention.